Hello and welcome. Today, we're going to demystify one of the most fundamental concepts in all of electricity, voltage. Think of this as our friendly guide to understanding the push that powers our world. Let's start with the quick bullet points. The first and most important idea is that voltage is the electric pressure that pushes electrons through a circuit. Let's break that down. Inside every wire, there are tiny particles called electrons. For electricity to happen, these electrons need to move, or flow. Voltage is the force, or pressure, that gets them moving. It's the oomph behind the electricity. A circuit is simply the complete path that the electrons travel along, from a power source like a battery, through something like a light bulb, and back to the source. Without voltage, the electrons would just sit there, and nothing would happen. We measure this electrical pressure in a unit called volts, named after the Italian physicist Alessandro Volta. The official symbol for voltage is a capital V. When an electrician or engineer needs to measure voltage, they use a special tool called a voltmeter. Now, this idea of pressure can be a bit abstract, so let's use the fantastic analogy shown here, the water analogy. This is perhaps the best way to visualize what voltage does. Imagine you have a water tank connected to a hose. The height of the water in the tank creates pressure. The more water you have stacked up, the higher the pressure at the bottom. This pressure is exactly like voltage. The actual flow of water through the hose is like the electric current. So, just remember, voltage is the pressure, and current is the flow. The image illustrates this perfectly. On the left, you see a tank with pressure, indicated by the gauge, but the pipe is closed. There's potential for flow, but no actual flow is happening. This is like a battery sitting on a table, full of voltage but not connected to anything, so no current flows. On the right, the valve is open. The pressure from the tank is now pushing the water out, creating a strong flow. This is like connecting the battery to a light bulb. The voltage pushes the electrons through the bulb, creating current and making it light up. Next, let's explore the types of voltage, because not all voltage is the same. There are two main types. The first is DC, which stands for direct current. As the name suggests, this is a voltage that is constant and always pushes the electrons in one single, direct path. The power from batteries, the USB port charging your phone, or the power adapter for your laptop are all examples of DC. The graph for DC voltage is a simple, straight horizontal line. This line shows that the voltage level stays the same over time. It doesn't fluctuate up or down. The second, and very common, type is AC, which stands for alternating current. This is the type of power that comes from the outlets in our homes. With AC, the voltage doesn't just push in one direction. Instead, it rapidly alternates, pushing forward, then pulling backward, over and over again. The graph for AC looks like a smooth, continuous wave, called a sine wave. It starts at zero, rises to a positive peak, falls back through zero to a negative peak, and then returns to zero to start the cycle all over again. In many parts of the world, this happens 50 or 60 times every second. This alternating nature is very efficient for transporting power over long distances, which is why it's used for our power grid. Finally, let's look at the basic formula and some key principles. The formal, scientific definition of voltage is energy divided by charge, written as V equals W divided by Q. Here, V is voltage, W stands for work or energy, measured in joules, and Q is the electric charge, measured in coulombs. In simple terms, this means voltage is a measure of how much energy each little packet of charge is carrying. It's crucial to understand that voltage causes current to flow. They are not the same thing. Voltage is the potential, the push. Current is the result, the flow. A very important point is that higher voltage equals more electric pressure, but it is not always more dangerous. What makes electricity dangerous is a combination of voltage and the amount of current that flows through a body. A static shock can be thousands of volts, but the current is so tiny and brief that it's usually harmless. A wall outlet has much lower voltage but can supply enough current to be lethal. Lastly, voltage is a star player in the most famous rule in electronics, Ohm's law. This law states that voltage equals current multiplied by resistance, V equals I times R. Resistance, R, is the opposition to the flow of current. Ohm's law shows us the beautiful, predictable relationship between the push, voltage, the flow, current, and the opposition to that flow, resistance, in any circuit. So, in summary, voltage is the fundamental driving force, the electric pressure that makes everything in our electronic world go. Whether it's the steady push from a DC battery or the alternating rhythm of AC from our walls, without voltage, there is no flow of electricity.